All right. So suppose the ski patrol lowers a rescue sled and victim having a total mass of 90 kg down a 60-degree slope at constant speed as shown below. The coefficient of friction between the sled and the snow is 0.1, and that's kinetic coefficient of friction. Okay. How much work is done by friction as the sled moves 30 meters along the hill, and so on. All right. Now, of course, since it's moving at constant velocity, the net force on the object is 0, and all that. But right, part A, how much work is done by the friction force? So we'll have to find the friction force. Let's look at the object. So we'll represent it by a point. Here is the weight of the sled and the patient. This is mg sine theta. This component is mg cosine theta. So the normal force is equal to that. And there is the kinetic friction force, which is mu k times the normal force. Okay. So the friction force, the kinetic friction force is mu k times the normal force, and the normal force is equal to that, is equal to mg cosine theta. Why is that equal to that? Because this guy is not moving in this direction, so in that direction the net force is 0. Okay, so this minus that is 0, and so that's equal to that. So this is equal to mu k times mg cosine theta. Okay. Now we have found the friction force, and the displacement of the person is along the incline. Okay. So, and the angle between the friction force and the displacement is 180 degrees. Okay. So work done by the friction force is that, which is Fk times S times cosine 180 degrees. Yep. So work done by the friction force is minus Fk times the displacement. Cosine 180 is minus 1. Okay. I showed that all to you in detail, but friction force always does negative work. Friction forces are always opposite to the displacement. The angle is always 180 degrees, and cosine 180 is minus 1. Okay. So, as you get more and more practice, you can write this equation directly. Okay. Friction force always does negative. Yeah, negative. So the definition of work is the definition of work, is F dot S, the force dotted with the displacement, which is Fs cosine theta. Here is the general definition. Okay, and so for a friction force, the friction force is always opposite to the displacement vector, and that angle is always 180. And cosine 180 is minus 1. Okay. So again, friction force always does negative work. Okay, so now let's calculate how much work is done by friction force as the sled moves down 30 meters. Okay, now we can put in the numbers. 0.1, 90 kgs, 9.8 meters per second square. Cosine 60, and that is, the displacement is 30 meters. Okay. So, I forgot my calculator today. So that's how much work friction does. Okay, minus 1,323 joules. Yep. Now let's now let's look at part B. How much work is done by the rope on the sled in this distance? Okay, so there's the tension in the rope. So now let's write down all the forces. Okay. So here is mg sine theta, friction force, and the tension in the rope. Okay, so mg sine theta, so let's choose this direction to be positive, down the slope to be positive. Okay, and in that direction, mg sine theta minus fk minus tension must be 0. Why should it be 0? Yeah, it's moving at constant velocity, it's not accelerating. Okay, so tension is mg sine theta minus fk. Okay, and the work done by tension again, so tension is in that direction and the displacement is in this direction. Again, the angle is 180 degrees. So work done by tension, oops. Okay, so, well, maybe we'd better calculate tension separately. Let me calculate tension over here. It's mg sine theta minus mu k mg cosine theta. 90 times 9.8 sine 60 minus 0.1 times cosine 60. And this works out to, let me have somebody's calculator. This is, okay, so the tension is 720 newtons, so this is minus TS minus 720, 30 meters. So the work done by the tension in the rope is minus 21,000 joules. Now compare this to the work done by friction, which is 1,300 joules. So friction is doing only about 5% of the work that tension is doing. So the fire rescue guy is doing all the work. Okay? And you're doing negative work because you're slowing him down. Okay? You're breaking him down. You're gently bringing him down. All right. What is the work done by the gravitational force on the sled? Okay. So let's find the work done by gravity. And there is mg sine theta s. Okay. Work done by gravity is, okay, so the gravitational force mg, there was the gravitational force we took the component of gravity in this direction and that direction. This force is equal to this force plus that force. That force does work. This force does no work. Why does this component do no work?
Because he's not moving in the y direction. He's staying on the surface.
Also, this force is 90 degrees to the displacement, is perpendicular to the displacement, and that's why that force doesn't do any work. Okay, so remember, the work done by any force is force times displacement times the angle between them, and if this angle is 90 degrees, cosine of 90 is 0. Okay, all right, so okay, let me do it two different ways. Okay. Here is theta. Here is mg. This angle is 90 minus theta. Here is the displacement. Okay, so the work done by gravity is force of gravity dotted with displacement. And force of gravity would be mg s cosine 90 minus theta. And this is mg sine theta. Cosine 90 minus theta is sine theta. Okay. All right, so there is the work done by gravity using that formula. Also, you can write it like this. So I don't know if I'm confusing you, but I'm just showing you two different ways of doing it. Here's gravity, and it can be broken up into two components, mg sine theta and mg cosine theta. And this component does no work, only this component does work, and that component is parallel to the displacement. So that will do, work will be mg sine theta times s times cosine of 0, which is mg sine theta times s. Okay, that component was parallel to the displacement. Anyway, the work done by gravity is mg sine theta s. You guys understand? How are you guys doing, my friend? Good. All right. So this is work done by gravity is 90 kgs times 9.8 meters per second square times sine 30 meters times sine 60. And the work done by gravity is 22,915 joules. Okay. Work done by gravity is positive. Okay. All right. Now, in part D, what they ask you is what is the total work done? Okay. So let me add a page below. Okay, and so now we'll draw this guy. Friction force and tension force. Okay, so these were the forces acting on the object. Okay, and the work energy theorem says the net work done, it shows up as change in kinetic energy. Okay, in this problem, they tell you you're lowering this guy at constant velocity. So when he's at the bottom, his final kinetic energy is the same as his initial kinetic energy. His kinetic energy did not change. Okay?
Because the velocity was constant.
The velocity was constant. 1/2, so I'll write it down just for you, my friend. All right? So V final is V initial, and that is equal to 0. So, okay? So work done by gravity plus work done by friction plus work done by tension should add up to 0. Okay. Now, so this is just a cross check. We have independently calculated each one of those. So let's add them up. So work done by gravity was so this is just a cross check. Work done by gravity was 22,915 joules. Work done by friction was 1,323 joules. And work done by tension was minus 21,592 joules. And does this add up to 0? All right. So even rounding errors canceled off. Okay. So if an object is moving at constant velocity, all the forces acting on the object put together, the net work done is 0. Okay. All right. So, this is chapter 7, right?